you have a system of linear equations, and your job was to make it easier to read off the solutions, if there are any, to that system. And so these systems just magically appeared. You didn't really come up with your own system of equations. And so, for example, here's pretty simple. So why is this called linear, by the way?
Because there are no x.
Exactly, right. We're not doing, we're just, all we're doing to the variables is multiplying them by numbers. We're not squaring the variables. The variables are not multiplying themselves. There's not taking cosines or some funky functions of these variables. It's just a simple combination. And so how did we deal with such a system? What was the idea? Well, the idea is to make the system sparse, right? Introduce many zeros so as to make the analyzing the solutions, if there are any, simple. And so the shorthand for manipulating the system was the augmented matrix. Where we took the matrix of coefficients, those are the coefficients multiplying my variables, put them in an array, and then augment that with the right-hand side of my equations. So we usually write that. In practice, you leave this off, right? But it's good to remind yourself that this is really a shorthand for this, where we don't write down the variables. So the first column corresponded to coefficients for x. This corresponds to coefficients for y and z. And this is the right-hand side of your system. Okay. And so how did we reduce this matrix? Well, we were told that we can only use 3 types of operations. So the 3 types of row operations are called elementary row operations. And the first one, I mean, we should be able to justify to our friends why these are allowed. It's pretty simple, right? It says exchange 2 rows. And of course, that's just rewriting the system where the equations are written in different order. So clearly, that won't change the solution to the original system, right? The second row operation was where you can scale, you can multiply a row by a number, and well, with one exception, what number would you not want to multiply a row by? Because that's kind of like just throwing out the whole equation, right? So you're losing information. Yeah. And of course that's justified because you're just multiplying both sides of the equation by the same onto your number. So that doesn't change the solution to the original system. And thirdly, we have the operation by which we add to a row a multiple of another row. In order to replace the row we're adding to, right? With each row operation, we're just going to replace one row. So, and why does this not change the system, the solution to the original system? Well, because if you when you multiply a row by a number, you're just multiplying both sides of the equation by the same quantity, and then you're adding to the same quantity to both sides of another equation, right? So it's just like you're adding the same thing to both sides of the equation, so it doesn't change the system. Okay. And we restrict ourselves to these operations because we don't we want a reduced matrix, but we want the solutions to the reduced matrix to be exactly the same as the solutions to the original, correct? Okay, so that's the idea. And we reduce the matrix, what's the procedure called? Well, there's two versions of it, right? There's Gaussian elimination, or Gauss elimination, by which we want to take the original matrix and turn it into a row echelon form matrix. Tell me if I'm spelling echelon.
Close enough for government work.
It's true, it's true. Can't deny that. And so a row echelon matrix, sometimes if you have a matrix A, you sometimes write REF, like for example your TI calculators that manipulate matrices have this function built in, reduced echelon form. And since it's been a couple weeks of class, I'm pretty confident you already know how to recognize the row echelon form matrix. But the idea is that when you reduce, if you have 0 rows, they go on the bottom. And any non-zero row, which that means a row that doesn't consist entirely of zeros, the first non-zero number is a 1. So the first non-zero number is a 1. And in a row echelon form matrix, if a column has a leading 1, then everything below it is zeroed out, right? Okay. But the stuff above a leading 1 doesn't have to be zeroed out. Okay, so this is an example of row echelon form matrix. The second method is Gauss-Jordan elimination. So Gauss-Jordan is, Gauss-Jordan elimination makes your matrix even sparser and introduces even more zeros. And the procedure takes a matrix and gives you a reduced row echelon matrix. Right? That extra reduced piece means just more zeros. And if you're using your TI calculator or even things like MATLAB, this procedure will take matrix A and return the reduced row echelon form of the matrix. And you write that. So, yeah, reduced row echelon form matrix, of course, says it's row echelon form in the first place, right? Everything below your leading 1 is zeroed out, but also everything above your leading 1 is zeroed out. So which number needs to be zeroed out? 2, right? So that's an example. It's reduced row echelon form matrix. Now, given a matrix A, the reduced echelon form of the matrix is not unique. Yeah, so the same matrix A might have 2 different row echelon form matrices, right? It's not unique because, I mean, if I have, for example, if I have this, well, that was a 2. Of course, I can say multiply, or to row 1, I can add 2 times row 2, correct? So, So both of these matrices are in row echelon form, but they're different. So the starting matrix doesn't have a unique row echelon form. Okay. What's important about reduced row echelon form, besides that it's the sparsest matrix you'll get for your system, is that it's unique, right? Given a matrix A, if you have a reduced row echelon form matrix, it looks just one way. Nothing else qualifies. Okay. All right. I was going to do this one, but I want to save time. So let's talk about, or maybe do an example, right? Like let's think of an example where we come up with our own system of linear equations. And an example of that is polynomial fitting. So let's fit a polynomial to some points, or curve fitting. So conceptually, if you have 2 points in the plane, what kind of polynomial would you like to fit it with? So if you have 2 points, okay, what kind of polynomial would go through those points? It's a line. Okay, so it's a polynomial of degree. So if you have 3 points, in general, what kind of polynomial would you like to fit it with?
Parabola.
Right, so a polynomial could be 2 or quadratic. And the graph is a parabola, that's right. And if you have 4 points, right, you won't necessarily get a parabola going through those 4 points, right? It's not guaranteed. You're guaranteed that there is a cubic that will go through 4 points that are not all, vertically lined up. And so on, right? If you had 1,000 points, what degree polynomial would you use? Uh,
1001.
999. Right, 2 points, degree 1. 3 points, degree 2. 4 points, degree 3. Oh. All right, so let's go ahead and do one. So suppose you need to fit a polynomial through the following 4 points. Why not? Let's find polynomial. Containing the following points. Well, it's 4 points. I'm guaranteed that there's some cubic. Yeah, none of these points are like on top of each other vertically, so I can fit a function. So I'm going to assume a polynomial of degree 3. Well, degree 3. There we go. And I'm going to write these out in really, maybe we're not used to this conventional, you write the powers of x in ascending order. But it makes the matrix you get easier to deal with. So I'm going to write this. And that gives me some y value, right? And each of these points is an xy pair in the plane. And so since we would like our cubic to contain these points, right? We know that this says that if x is -2, y should be 0. This gives us license to plug those in. So if we replace x with -2, and we know that we want y to be 0. So for each point we get an equation, a linear equation, where the unknowns are not x and y, but the unknowns are rather these coefficients in my polynomial. So x is 1, and y has to be 0, x is 2. And x is 4. Oops, this is 16. And 4 cubed is 64. So, yeah. So we get a system of equations, correct? And our job is to solve these unknown coefficients. So we use the method of creating an augmented matrix. And it's row reducing. So the corresponding matrix would be the matrix of coefficients. Augmented is the right-hand side of my system. I'll have it. Let me start row reducing, and the elimination methods are algorithms. Like a computer could do this blindly. And we start with at the top left, we insist that this is going to be a 1 if possible, right? So we introduce a leading 1, and we already have a 1. In some books, this would be called a pivot. In your book, it's called the leading 1. And sometimes it's called the pivot because you use it to zero stuff out in that column, right? And you use this row operation. The third one I wrote down, which was to a row add a multiple of another row, right? Because to decide, and so if you zero this out and you ask yourself, what do I add to a negative? What do I add to 1 to get 0? Negative 1, right? And so so what you do is you say, well, to row 2, I'm going to add negative 1 times row 1 in this case, because you want to multiply the row that has the pivot, right? You use it as a way of introducing the number you need to add to get 0. Okay. So likewise, I need to add a negative 1 to turn this into a 0. So to row 3, I'm going to add negative 1 times the row which contains my pivot. And then likewise, to row 4, add negative 1 times row 1. And that's where my pivot is. And you get the following matrix. And of course, so notice that in deciding what row operation to do, we're just looking at the first column. But of course, we have to apply the row operation across all entries in a row. So, yeah. And of course, I'm saving time. I'm not going to do 3 different steps separately. I'm going to use 3. So, okay, subtract. I might have to, at some point, give you the final reduced matrix. This takes a long time. All right, cool. So we're done with the first column, right? So we move over a column and down 1 row, and then get a 1 over here. Okay. And of course, the quickest way is to use the second row operation. I mean, you can always exchange rows, right? If I had a 1 over here, I would maybe exchange row 2 and 3. But if that doesn't work, as long as this number is non-zero, I can use the second type of row operation that I wrote down, namely scale a row by a non-zero number. So you ask yourself, what do I need to multiply 3 by to get 1? 1/3. It's reciprocal, right? So this suggests that we should multiply row 2 by 1/3 to get a 1. And just for simplicity's sake, notice that all these are divisible by 4. So I'll go ahead and scale row 3 by quarters. And these are all divisible by 6. So of course you get fractions in, but not in this case. So who's afraid of fractions, right? Okay, so I scaled all of the last 3 rows, and I get this result. Alright, so let's continue. So now we have our pivot, our leading one. We're going to use it to zero everything out. If I was doing just Gauss elimination, Gauss is the guy who zeroes everything down below the leading one. Jordan is the guy who zeroes everything out above, right? So was somebody raising their hand? Okay. So I'm going to use my pivot to zero everything out. Okay, so to -2, I would like to add a 2 to get 0 over here. And we're just focusing on the second column to decide which row operation to use. So to row 1 we add, right, 2 times row 2, because row 2 is the row containing my pivot. And to row 3 we add a negative row 2. So, and we're almost done, so bear with me. Well, it looks like we're done with the second column. It definitely looks like the column of the identity matrix. Right? So we move over a column down 1 row and get a 1 over here. But behold, it's already a 1. So we just have to zero everything out. And we're using Gauss-Jordan because I'm zeroing everything out in that column except my pivot. So I need to add a -2 over here. So to row 1, I'm going to add -2 times row 3 where my pivot resides. I would add row 3 to row 2 and replace it. And I could have scaled by 1/3 here, but oops, almost messed up there. Right, I need to add a -3 here, so I'll multiply row 3 by -3. And we're almost home. All right, now this. Oh yeah, we get 6, 6. So I would introduce 1 here by scaling row 4 by 6. To get 1, 1. And then use that leading 1 to zero everything out. Is it okay if I just jump to the conclusion? I know I'm kind of aware of the fact that I'm also recording this, so usually I would say, hey, are you guys ready to move on? But I need to be thorough enough here. But here we go. This is the reduced row echelon form of the matrix. Yeah, we don't have any 0 rows, but yeah, the first non-zero entry is a 1. Everything with every column with a leading 1 is zeroed out. Okay. All right, so let's recall. Let's just always remember, if you have trouble getting the solutions or reading the solutions, off the reduced matrix, this is just shorthand for system of equations, right? So my unknowns were the coefficients in this cubic. And so the first row can be interpreted as saying 1 times A naught plus 0 times A1 plus 0 times A2 plus 0 times A3 is equal to the right-hand side, right? So we know A naught is 4. Likewise, these coefficients are multiplying my unknown, so I get A1 is equal to the right-hand side. A2 is 0, and A3 is 1. Okay, so we've solved, yeah? This is definitely a simpler system to solve. So now we have our cubic. We have A naught, the constant, so plus A1 times, negative 3 times x, 0 times x squared, plus x cubed. So that's a cubic that contains all the 4 points that we originally listed. All right. Any questions about that? Now, before we move on to the new material, let's discuss the nature of the number of solutions in a linear system. What are the 3 possibilities for the number of solutions in a linear system? It's one possibility, unique, that's right. Or none. So none, 0, exactly 1, or many, infinitely many. And the question is, how do we know which case we're dealing with? Well, again, we reduce the matrix. So the number of solutions, right, in this linear system. He said no solutions. Exactly one solution, a unique solution, or infinitely many. All right. So let's think of a reduced matrix where you have no solutions. What would it have to look like? Okay, I'll bet it is. Right. So this is an augmented matrix, remember, right? We're not just looking at some mathematical object called matrix, it's an augmented matrix. So this represents a system of equations. How do we know there are no solutions here? Well, you interpret the last row as saying that if my, let's say, unknowns are x1, x2, x3, x4, and this is the right-hand side, then you interpret that the last row as saying 0 times x1 plus 0 times x2, and so on. It's 3, right? Well, obviously this says 0 equals 3, which is false. It's a contradiction. So there are no values for the unknowns that would make that true. So there are no solutions. So in short, if you have a row of zeros here in your coefficient matrix, right? But on the right-hand side you have non-zero, you know you have no solutions. All right, and how would we know we have... So, okay, oh yeah, and what do you call, what's the name for a system with no solutions? What do we say?
Inconsistent.
Inconsistent, right? Like somebody's story is inconsistent, it doesn't match up, like it's not consistent, so inconsistent. And so this is inconsistent, and what do you call these cases where we do have at least one solution? Inconsistent, makes sense. Consistent system. So let's see. So now that was inconsistent. Now let's look at a matrix where the system is consistent. So again, augmented matrix. So how do I know that I have infinitely many solutions? Well, one way I know is that I can read off the equations of this reduced matrix. So the last row just says 0 equals 0, which is true but not informative about the nature of the unknowns. So let's move on to the second row, which says that 1 times x2 plus 2 times x3 is 0. The first row says that x1 minus 4x3 is 1, right? So notice that I can easily solve for these in terms of x3. Okay. So here we have 3 unknowns but 2 equations, 2 independent equations. So that's not enough constraint. Yeah, we have more unknowns than independent equations or constraints. So we're going to get infinitely many solutions. All right, and so we're going to let one of the variables be a parameter. I guess technically it doesn't matter which one, but it's wise to let the unknown that corresponds to a column without a leading entry, right? So these 2 columns have a leading entry, this doesn't. So we're going to let that variable be a parameter. So we're going to say something like let x3 be, let's say t, where t is a real number. And then we see that x1 is completely defined. Replace x3 with t, and x2 is negative 2t. So all your solutions have this form. You get 1 plus 4t, negative 2t and t. Right, so you see, since there are infinitely many real numbers, we have infinitely many solutions. What else can I say about this that I wanted to mention? Oh yeah, okay. But you can also kind of, once you're familiar with this kind of procedure, you just say, well, I have 3 unknowns, but my matrix of coefficients in the augmented matrix only has 2 leading ones, right? So if you have a consistent system and you have less leading ones than you have unknowns, you have infinitely many solutions. So let's now look at a consistent system with a unique solution. How many, so let's say I have 3 unknowns, how many leading ones will I have in my example? Okay, so I'm looking at example of unique solution. I have 3, I'm going to assume 3 unknowns. How many leading ones would I want? Yeah, I'm holding my finger for some reason. So this would be easy. Yeah. Augmented matrix. You have 3 unknowns. You have 3 leading ones. So it's exactly 1 solution. What kind of system is guaranteed to have at least 1 solution? Homogeneous, right? So a homogeneous system is one where we have the right-hand side is all 0, right? So whatever. Okay. Right, so the right-hand side is all 0. This is called a homogeneous system. Much overused word in math, right? And so how do we know there's at least 1 solution? Because there's an obvious solution, and what's that obvious solution?
0 equals 0.
Well, no, the solution is that all 3 variables, or all the unknowns are 0. Right? That's obviously will satisfy this equation, so you'll never have the case of no solution in a homogeneous system. And what do we call this solution which is so obvious?
Trivial.
Trivial, okay. And any other solution where at least one of the variables is non-zero is non-trivial. Okay. So, and since you had two of these type of questions on your homework, I thought it's good to remind ourselves and keep reminding ourselves until the first exam. And this is not a hard version of the question. Let's suppose we have an augmented matrix representing some system, 3 equations, 3 unknowns. This is a short example. So. Right. And our instructions are to find all the find values of A, which such so that we get the following cases, right? Well, it's going to, since this does not represent homogeneous system, the right-hand sides are non-zero necessarily. So we can have inconsistent, consistent. We can have unique solution, or infinitely many solutions. Right? So what was the strategy here? Well, the strategy was to reduce this matrix. Yeah, it doesn't have to be reduced to row echelon form, but at least, let's say, upper triangular, so we just zero stuff out below the diagonals, so that it's sparser and it's easy to analyze the situation. So I'm going to start with this leading one to zero these guys out. All right, so we get, maybe I'll just, all right, so. So of course, when I multiply this by -3, I get 3, and I add it over here, so I'm going to get a squared plus 1 now, right? And so 2 times -3, -6, plus 8 gives me 8 plus 2. So now I'm not even going to bother to get this to be a 1, right? I just want to get some zeros here, so I'm going to zero this out using this too. So pivot to row 3, subtract from row 3, subtract row 2 to replace row 3. So now we get a squared plus 1 minus 5, so a squared minus 4. Okay. So it's pretty good. I mean, it's not even, I guess, row echelon form, but it's pretty sparse. So what do we want to see to have no solutions? Well, we want to see a row of zeros for the matrix of coefficients, but non-zero here, right? So this is, so we would want this to be 0. But simultaneously, a plus 2 not to be 0. So solving this, we see that this is 0 if a is 2 or a is -2. But which of these values makes this non-zero? 2. So we get an inconsistent system if a is 2. Okay. So what about a infinitely many solutions, probably easier to deal with. Can I just... So, well, that's the case where we'd want to have less leading entries in the coefficient matrix, and we have unknowns, so we want this to be a 0, and this to be 0 as well, so it's not as inconsistent, right? So we see that if A is -2, yeah, the solution to both of these, it's a nonlinear equation system, right? It's A squared. The solution here is A equals -2. So if A is -2, we get infinitely many solutions. And finally, for a unique solution, we'd want to have 3 leading entries, right? 3 leading entries in the matrix of coefficients, because we have 3 unknowns. So we would want this to be non-zero, right? And this is not 0 for any number A. And if this is non-zero, think of it this way. We can, we would have 3 leading entries. So that's not 0 for A, that's any real number not equal to 2 and not equal to -2, right? So any other real number. Yeah. All right, so that's just a reminder of that. Okay, well, let's move on to the new material. I don't know how much time I took. Yeah, it's a long time. Is there anything on the new homework that's of interest to you? Maybe I can...
Graph theory. Oh, yeah.
Graph theory.
And he just went over, well, Turi just went over yesterday and not a clue what in the world he was talking about.
Oh, yeah, all right. That's simple enough. So now, in this next homework, we're no longer looking at augmented matrices, right? It's no longer a representation or shorthand for system equations, but rather we're looking at matrices as mathematical objects in their own right, right? So now the matrices don't have to represent the system. Can we do? Well, I guess since in graph theory, it's part of it is setting up a matrix, adjacency matrix or vertex matrix, and then you have to raise it to various powers. Well, we have to know how to multiply matrices, right? Okay, so if you multiply matrices, I don't know what to say about this, how much to say about this. So a matrix has a size. It's the number of rows by some number of columns. Okay. And for the multiplication of 2 matrices to be defined, the number of columns in the left matrix has to match the number of rows in the right matrix. Right? These have to agree. If these agree, then the multiplication is defined, and then A times B will be a n by m matrix. Right? So, do a quick example. There we go. That's my quick example. Okay, so. Alright, so this is a 2 by 3 matrix, clearly 2 rows by 3 columns. B is a 3 by 3 matrix. Yeah. What do you call a matrix which has as many rows as columns?
Square.
Square matrix. All right, so A times B, is it defined? Yeah, right. 2 by 3 for A, B is 3 by 3. So the number of columns for matrix A matches the number of rows for matrix B. And what's the size of the resulting matrix? It'll be 2 by 3, right? All right. What about B times A? Is that defined? Yeah. 3 by 3. And this is a 2 by 3. The number of columns for the left matrix does not match the number of rows here, so not defined. So, of course, what does it mean to transpose a matrix? How would you describe it in words? Right, let's say A transpose, right? Well,
Flip it above the main diagonal.
yeah, yeah. So there's this kind of like notion of it, you fix these points, you lift these corners and kind of flip it, right? So another way to articulate it is that the rows of a matrix will become columns and the columns become rows. We'll also maybe look at index notation to show. Okay, so the first row, 1, 0, negative 2, becomes the first column of A transpose. The second row becomes the second column. And so clearly, if I take the transpose of the matrix and transpose it again, what would I get? The original, right? It's like flipping twice gets you back to the original configuration. So let's see. So even though B times A is not defined, B times A transpose, right? So if you have that A in general is an n by k matrix, then A transpose must be k by n, right? Because the columns became rows and the rows became columns. So B is 3 by 3. A transpose is 3 by 2 because the rows and columns were exchanged, and the resulting multiplication will be 3 by 2 matrix.
If you have, like say, a 3 matrix, ABC, that are transposed, would that be AT times BT times CT? Does that equal CT times BT times AT?
Oh yeah, so yeah, okay, I didn't really want to go into the properties of transposes, but that's a good question. So if you have A times B and this matrix multiplication is defined, and you want to transpose the product, what's the correct way to do this? Well, you transpose each matrix, but you also have to flip the order of multiplication. So this becomes B transpose times A transpose.
Okay.
And you can generalize this, right? If you have A, B, C, D, E transposed, these are all matrices, this is equivalent to E transpose, D transpose, C transpose.
So you have to reverse the order of the matrices
You
as
do,
well?
yeah.
Okay.
You can probably see that if you just analyze the dimensions or the sizes, right? So if you have a 2 by 7 matrix for A, and you have 7 by 3 matrix for B, this multiplication is defined. And if I transpose this, and this is incorrect, but if I claim that this is A transpose, B transpose, well, this is A transpose now is a 7 by 2 matrix, B transpose is a 3 by 7 matrix, so that's not even defined, right? So it just doesn't make sense. But the correct thing to do is say it's B transpose, A transpose, and the sizes are consistent, right? So B transpose is 3 by 7, B transpose is 7 by 2, so the resulting matrix would be 3 by 2. The original is 2 by 3, right? Which makes sense. If the product is 2 by 3, the transpose of the product should be 3 by 2. All right. I wanted to do an example that's similar to one of the homeworks I thought it was interesting. So can I ask you, does matrix multiplication, can you say in general that matrix multiplication commutes? Like multiplication of numbers is commutative, correct? So 5 times 2 is 2 times 5. So for real numbers, or complex numbers, whatever, number multiplication is commutative. But we know that in general, that's matrix multiplication. There are these mathematical objects where we define the multiplication between them. And we can't say in general that AB equals BA. It might for some pairs of matrices, but in general it doesn't hold. So matrix multiplication is not commutative in general. Commutative?
Commutative.
Thank you. All right, so by the way, if I look at square matrices, right? There's a subset of them that are special. It's called the identity. So this is a 2x2 identity. I guess this would be 3x3 identity. And in fact, that's kind of like our archetype for when we reduce a matrix. We like to get to as close to that as possible, right? These are identity matrices. And can we think of matrices that commute with every other matrix if you're talking about square matrices? Yes, that was very good. I didn't think about that one. The zero matrix commutes with everything. What other matrices would commute with everything? What's the identity matrix times any other square matrix? It's itself, right? This is called identity because it acts like the number 1 for matrix multiplication. You can easily show that the identity times any other matrix is equal to that matrix. It's the number, it's the matrix 1, yeah, for multiplication of matrices. And likewise, A times I is still A. So the identity has this special property, right? So an identity matrix is an example of a matrix that commutes with every other of its type, of a square matrix. So yeah, there are some matrices that will commute with every other matrix, right? And how can we somehow come up with, for square matrices, let's say 2x2 square matrices, can we come up with all possible matrices that commute with every other matrix? So we're going to find 2x2 matrices that commute with every other 2x2 matrix. That's important. Every other, not just some, but every other square matrix. How would we try to figure this out? It's pretty short. Well, I don't know what the square matrix would be that commutes with every other, but I do know that it would have, well, it's 2x2. Okay. And I want to commute with every other. Well, so what you can do is you can think of very simple matrices, 2x2 matrices, and these are the simple ones I'm thinking of. Right? If this matrix is to commute with every other square matrix, it would have to commute with this simple matrix. And it would have to commute with this simple matrix, and this one, and this one. And you'll later learn that you won't have to consider any of the possibilities. Right? The reason you won't have to consider any other possibilities is because every square matrix you'll be able to write as a combination of these. Right? If you look at this decomposition of this arbitrary 2x2 matrix, you see that every 2x2 matrix can be expressed as a linear as a combination of these. So really, you wouldn't have to consider any other matrix. Let me erase this junk here. All right. So let's see. Let's just use this matrix first to see what we can learn about these numbers. So we want our matrix to commute. Right? So we want our matrix times the simple one to equal that simple matrix times our matrix. And switch the order of multiplication. And what do we learn from this? Well, let's multiply. Right? So the result will be a 2 by 2 matrix. The 1, 1 entry is just the multiplication or dot product, if you will, of the first column and the first row. So A plus 0 times B, so we just get A. Of course, then we have A times 0 plus B times 0, C plus 0, 0 plus 0 is 0. And this would be A, B, 0, 0. So what have we learned from this? Well, of course, these matrices are equal only if the corresponding components are equal. So this tells me that, well, A equals A, that's known information, but 0 equals B, right? So we learned that much. And C equals 0. So right away, just by looking at a simple matrix, we see that the only matrices that will commute with every other matrix are the ones which have zeros for entries that are not in the diagonal. All right, so then we can move on, and let's maybe use another simple matrix. I think we got all the information we could from this. I don't know, let's use this simple matrix. Right, and let's update this guy. We've learned that B and C are all both 0. And I'll cut this example short. So we get 0, A, 0, 0. And then 0, D, 0. Okay. So from here I learned that A has to equal D. And if you go on, you can show that that's sufficient, right? So only matrices that look like this will commute with every other matrix. So these are diagonal matrices. That is to say, only the non-diagonal entries are always 0. And these diagonal entries have to be the same. But that matrix will commute with everything else. But no others, right? No other types will commute with everything. So let's play logic. Is there a matrix that doesn't commute, a 2 by 2 matrix that doesn't commute with any other matrix?
All zeros in the diagonals and then the same values in the non-diagonals?
So, no, all matrices will commute with at least one type of matrix, right? Namely the identity. So there is no matrix that doesn't commute with anything. But so that was just a silly logic game, so I apologize. Okay. Right, but we also have matrices that might not commute with everything, but they might commute with some matrices. So here's an example of a square matrix. Let's call that A. And it doesn't commute with everything, but it does commute with some matrices. So how would we find all the matrices, let's call them X, such that A commutes with all these X's? So AX equals XA. How do you find such matrices? Well, again, very similar to over there. We don't know what X is, but we know it's going to be a 2 by 2 matrix. Let's try to figure out what these values are. And this tells you how to set up a system of equations, right? Because we have 8 times X is X times A. Alright, so we multiply these up. The result is a 2 by 2 matrix, but I want some space here, so 1 times x1 plus 3 times x3. Okay, the 1, 2 entry here will be the first row, second column multiplied, so x2 plus 3 times x4, and so on. So the 2, 1 entries, second row times first column, so 2x1 minus 4x3, then 2x2 minus 4x4. And that should be the same as this result, right? So x1 plus 2 times x2, 3 times x1 minus 4x2. And again, right, these matrices are equal, so the corresponding entries are equal. And I won't solve the system because, that's, but you see how we get a system of equations, right? The system looks like this. x1 plus 3x3, the 1, 1 entry here has to equal the 1, 1 entry here. Then let's get the 2, 1 entries and let's equate those. And the 2, 1 entries. So every time we equate the entries, we get a linear equation. And then, of course, now to write this in standard form, we're going to bring all the constants, variable stuff to the left side and leave the constants on the other side. So I get, of course, the x1s add to you can subtract them off on both sides. All right, I'd probably bring everything to the right here, but whatever. So, by the way, what kind of system am I going to get? Yeah, right? So, that's another way of seeing, I don't know what I just wrote there. That's another way of seeing that we have at least one solution, namely the zero matrix is the trivial solution that's guaranteed here. So, I don't know why I'm getting lost here. Okay. So that's your system. The corresponding matrix is and I'll let you solve this. I guess I'll give you the solutions. But if you, that's our augmented matrix, let's call it M. Then the reduced row echelon form of that matrix is you see right away that these two rows are the same, so you can, well, they're negatives to one another, so you can add one to the other. you at least get 1 row of zeros. We ended up with 2 rows of zeros. Right. So we have infinity solutions, right? 4 unknowns, x1 through x4, but only 2 leading entries in my matrix of coefficients. So, and here I would let the free variables, so those are the ones that correspond with columns with no leading entries, are x3, x4. So we would let these be some real numbers. And then we can easily solve for x1 and x2 in terms. x2 is 3/2 of r. So that would be, so now you can choose any numbers you want for r and t, and you'll get a matrix that it's guaranteed to commute with a. So that should be similar to the homework example. Let's move on to, unless you have questions. Let's look at some graph stuff. Right, so you're discussing directed graphs and undirected graphs, and something called the vertex matrix or adjacency matrix. Do I need to sign the sheet?
Yes.
I'm going to pass around this sign sheet. All right, so let's look at a directed graph. So this is where you have nodes or vertices with possibly edges connecting them, and the edges have a direction. So all right. So I guess I would use V for vertex, but whatever. P for point. Okay. So we can create. So you see that we have 5 vertices, and some of these are connected by edges and they're directed, right? So I can see that this tells me if I'm at P1, I can move to P3, but I can't go backwards in one step, right? Because it's one direction. Now we can create something called the vertex matrix. M. And the entries of M are defined this way, so let's get used to this more abstract notation. The ijth entry of our matrix, so in the ith row, jth column, is either 1 or 0. What do you think? When will it be 1? Do you think? Like so, if I ask you M1, 3, do you think that's going to be equal to 1 or 0? It says that if I can get from vertex I to vertex j, then I indicate that with a 1. Right? So if there's an edge from pi to p2. And 0 if you can't get, right? I don't know how to write that. I don't want to articulate it right now. But yeah, if you can't get from pi, pj in one step. So for example, M31, that would be 0, correct? Because I can't get from vertex 3 to vertex 1 in this step. And likewise, M1, 4. And there's no directed edge directly from vertex 1 to 4. I hope that's clear. Okay. Right, so given such a directed graph, you should be able to come up with a vertex matrix. So our vertex matrix is going to be how large? Well, this matrix just indicates whether there's an edge between pairs of vertices. Since we have 5 vertices, we're going to have a 5 by 5 matrix. Okay, where you have like row 1, 2, 3, 4, 5, column 1, 2, 3, 4, 5, right? Because we need to indicate all possible, edges, directed edges from one of the 5 vertices to the other 5 vertices. So and we should be able to populate this matrix with zeros and ones. So I would just start at, say, vertex 1. Can we get to, so you tell me, we are not allowing to go from a vertex to itself, right? If we did, we would be writing something like this. This would indicate that there's an edge from vertex 1 to vertex 1. We're not including those. Right? So if we're not allowing that we can go from P1 to P1 in a step, what do we know about the diagonals of this matrix?
Zeros.
Right, and okay, so tell me, vertex 1 to vertex 2 is their directed edge. 1 to 3?
Yes.
1 to 4?
No.
1 to 5?
Yes. No.
No. Maybe I should also check on your paper. Yeah, no. So that's all right. Now vertex 2. Can we get to 1? Yeah. Well, 2 to 2, that's not allowed in these problems. 2 to 3? No? Yeah. 2 to 4? And 2 to 5, okay. Then 3 to 1, no. 3 to 2, yeah. No, yeah. Okay. So 5 vertices, you get a 5 by 5 vertex matrix. Now, so what does this matrix M tell me? Well, it says, can I go from one vertex to another one step? Okay. And if you square this matrix, right, so take the matrix times itself. I used a calculator for obvious reasons. And by the way, if you're given a vertex matrix, you should be able to draw a graph as well, right? Okay, so now once you square this matrix, which initially was full of zeros and ones, you can have non-zero entries now. Will I get negative entries? Not possible, because you're only multiplying zeros and positive numbers, so you're never adding negative numbers together. Yeah, 1, 1, 1, 1, 2. All right. So what do these numbers tell us? So yeah, the diagonals are no longer necessarily 0. But so this matrix tells us how many paths there are. So M2 will tell us the number of paths consisting of 2 steps, right? Or path of length 2. I don't know, consisting of 2 steps. So that means you go from vertex to another, traversing 2 edges. 2-step paths. two-step. So it tells me the number of two-step paths. Okay. So this tells me that I can get from vertex 5 back to vertex 5 in 2 steps, in 2 different ways. Okay. So let's see. Why would that be? Well, I hope it's clear, right? You can go from vertex 5 to vertex 2, so that's step 1, and back. So that's 2 steps. Likewise, vertex 5 to 3, and then back to 5. So let's see, were there numbers that were non-zero initially? Yeah, like right here. So you can go from 2 to 5 in 1 step, but you can't go from 2 to 5 in 2 steps. Right? 5, right? Because there's no like, no, you can't. Like, yeah. Right. So what will n cubed tell me? It's the number of 3-step paths from a vertex to a vertex, n to the 4th, and so on. So I mean, that's number theory, but I mean that's graph theory, but he left. I don't know what else to say about that. That's all there is. So you can compute higher and higher powers. So in general, right, how do we define m to the power k? Right, it consists of entries. So you write the ij entry of m of the matrix m raised to the power k, and this tells you the number tells you the number of k step paths from vertex. I to vertex j. Okay, what about an undirected graph? So this is where we have edges between vertices. And it's implied that you can go either direction, essentially. So it's like a directed graph where every edge is a two-way street, right? With a directed graph, it's a two-way street or a one-way street. It could be either. Well, actually, let's cut it off here.
If you came in late, I need to see you.